All right. Thanks a lot, Kay, for the introduction, and thank you for the organizers for the invitation to be here today. I'm going to talk about this idea of loss versus fair for Dutch auctions, and this is joint work with Dan Robinson from Paradigm. Dutch auctions are primitive we see often in DeFi. I would say, probably AMMs are the number one most popular primitive, but Dutch auctions maybe a close second. Some places where you see them is they're at the heart of things like routing trades in requests for quote or RFQ protocols. So something like, let's say, Uniswap X, that's a complex protocol with many pieces, but one piece of it is that an order may be, you may try to get an order filled by releasing it as a Dutch auction, right? So have a price descending over time and wait for the first filler to trade against it. Also often used in liquidations and protocols like Maker. The idea here is maybe you have some bad debt. You need to sort of sell the collateral and recover that debt. And so again, a Dutch auction can be used. Also used in other types of things, in peer-to-peer lending protocols, in protocols like Euler and so on. Why are they so popular? They're easy to implement. You can easily implement it as a smart contract where you accept a price based on the calendar time or the block number or whatever. And indeed, once that smart contract is live, it only requires one transaction to clear, a buyer who arrives at the right time and is willing to pay the right price. This means that people who don't win typically do not need to pay any transaction fees or reveal that they were even interested with this minor proviso that maybe if you have multiple trades, multiple bids on the same block, maybe you might see the failed bids in that case. In terms of computation and communication complexity, they're also relatively simple. Again, you only need to look at this one a winning bid, compare that to a first price auction, let's say, where you need to collect a bunch of them and maybe take a maximum and so on. Tim's recent work with his co-authors argues that there are one class of auctions which are strongly shield-proof. This is the idea that the auctioneer cannot increase the value they obtain through artificial or shield bids. And in an environment like the blockchain, where it's highly anonymous, that's an important property. And other variations have been proposed. So one thing we'll talk about in a little bit is the idea of a gradual Dutch auction, where you're not selling, just having a single auction at one instant in time with the price decreasing, but maybe you're continuously selling over a long period of time, emitting many auctions in a sort of a constant, continuous way, sort of analogous maybe to the idea of a TWAP order or VWAP order in traditional finance. So what we're going to do today is we're going to analyze Dutch auctions and gradual Dutch auctions. This is going to be pretty different than sort of the typical kind of auction theory analysis. It's going to be different because we're going to be operating mainly in a common value setting, right? And in a setting where everybody has the same value for this object. And this is a setting that makes a lot of sense in financial settings where the thing you're trading might, literally be bought and sold at the same time on exchanges and so on, right? So we're going to imagine a setting where everybody has a common value for the item. And that common value is observable. And also our setting is going to be dynamic. So we're going to be operating under the framework of the Black-Scholes model in terms of the that common value process evolving. And it's going to be adapted to the blockchain setting in that we're also going to incorporate the fact that in blockchains, you can't trade in continuous time, but you can only trade at discrete instances in time when blocks are being generated. In that framework, we're going to identify this notion of loss versus fair. This is the expected value leakage to the seller from the buyers because of the fact of that the blocks are discrete. This is kind of very analogous to the idea of loss versus rebalancing AMMs, also analogous to the idea of high frequency trading quote sniping in sort of TradFi markets. And we're going to basically quantify the value of this type of MEV in terms of the MEV associated with Dutch auctions. We're going to find closed form expressions for this MEV, what we call a loss versus fair. They're going to depend on two different sets of parameters. One set of parameters is going to be things that are intrinsic either to the thing that's being auctioned or the blockchain. So importantly, volatility of the asset is going to be very important. Also the mean block time, but it's also going to depend on parameters of the auction that can be chosen by the seller. And the two parameters for a Dutch auction are how fast do you adjust the prices, how fast do you decrease the prices, namely, sort of the price drift, and also maybe the initial mispricing, right? So where do you start the auction relative to where you believe the prices are? And the formulas we're going to obtain are going to be relatively simple and easily computable. So you can make statements like if the daily volatility is 5% and you have 12-second blocks and you're lowering your prices like 1 basis point a second and you start 10 basis points above where you think the fair price is, then maybe you lose 13 basis points in this efficiency cost that I'll define. And it would take, maybe 23 seconds on average for your order to get filled. So we're going to be able to compute these types of quantities, the efficiency loss, and then some kind of a measure of how long it takes to trade and how fast it is to trade. And in general, we're going to see there's a trade-off. Right, when you pick your auction parameters, for example, your price drift, if you make your price drift very slow, we will see that that's going to mitigate your efficiency loss, the loss versus fair. On the other hand, it will take a long time to execute. Right, so we're going to see this sort of a fundamental trade-off between efficiency losses and throughputs, and the theory is set up here in a way where, in a very practical sense, it can guide parameter choices for these auctions. Okay, so I'll just skip the literature review in the interest of time. It's in the paper. Let me dive into the model. The TLDR is we're going to closely follow the Black-Scholes setup of the lever papers. Namely, we're going to imagine we're trading a risky asset versus a numeraire. So the risky asset, you can imagine something like ETH versus the numeraire being a USDC. Without loss of generality, we're also going to imagine there's zero interest rates. Again, this makes a lot of practical sense because the environments we're working on, we're thinking of timescales on the order of maybe minutes or seconds, or and interest rates don't matter on that kind of timescale. As I mentioned already, we're going to be in a common value setting. Right, so we're going to imagine that there's some price process, P of T, that prices the risky asset in terms of units of the numeraire or cash asset. And we might imagine that this might be, let's say you're doing an on-chain auction of ETH versus USDC. You might have in the back of your mind, well, what is the price on Binance, where it's sort of a deep and liquid market where these assets trade. Again, this highlights a common value setting. It also highlights that we're not addressing the question of price discovery, right? We're imagining here the auction is being used to sort of get a fair price, but the price discovery is happening somewhere else and is exogenous to our model. And so just to sort of describe that risky asset price process, we're going to use basically the standard setup in continuous time finance since the time of Black-Scholes. And in particular, we're going to assume that the risky asset follows a geometric Brownian motion. So what I've written here is we're looking at like the instantaneous return. You can imagine the return over a very short time horizon. It has two components. One is a deterministic component, which is a drift, right? So here, for example, we're thinking of Ethereum. Maybe the market belief is that the price is going up over time. So maybe you have a positive drift over here. But more importantly, from our perspective, there's a lot of randomness, right? And so the stochastic component is the second part of this stochastic differential equation. We imagine we have a volatility term where you have sort of a volatility of returns multiplying a Brownian increment. So again, this is the most standard model in quantitative finance in terms of modeling asset prices. But for those who haven't seen it, you can sort of imagine this as a model where over very short time horizons, the relative returns are distributed according to a normal distribution. So that's our basic setup. So without loss of generality, we're imagining that we have an auctioneer who wants to sell an asset via a Dutch auction. So in particular, they're going to start listing at a high price, and the price is going to be decaying. This is without loss of generality. We could do everything in the buying case. In the buying case, you'd start at a low price, and you'd sort of raise the price you're willing to pay until you reach a price at which someone sells to you at that price. I will, however, briefly note that the formulas are asymmetric in the two cases, because at its heart, geometric Brownian motion is asymmetric, right? So for example, if an asset is distributed according to geometric Brownian motion, the price can go up to infinity, but it can only go down to zero, right? Because asset prices are sort of positive. So the formulas will be slightly different, but it's also not material on the kind of timeframes that we're thinking about. Again, we're imagining these auctions happening in seconds, minutes, maybe hours, not months or years. So we're going to be selling. We're going to let A of T be the current asking price. And, a Dutch auction, that asking price has to be decreasing over time. And so we're going to decrease it in a deterministic way. And the way we're going to decrease it is that it's going to be geometrically decaying, right? So the price A of T will be exponentially or geometrically decaying. Lambda greater than 0 is going to be the decay rate. And this is in the context of geometric Brownian motion, for reasons which we'll see in a moment, the most natural thing to do. You could also consider an alternative model where maybe you have linearly decaying ask price. So dA of t equals minus lambda dt, no term down here, and that would pair well with a fair price that's just arithmetic Brownian motion, not geometric Brownian motion. But again, over short time scales, seconds, minutes, hours, geometric Brownian motion versus arithmetic Brownian motion, it really doesn't make a difference. And this particular choice maps better to the modeling assumption of geometric Brownian motion. Again, is a standard choice in finance. So that's our ask price. And one very useful alternative way to sort of think about these is the idea of a mispricing process that's Z of t. So this is going to be the difference in the log prices between the offered price and the current fair value of the asset. And this is where pairing geometric Brownian motion with geometric decays works well, because this process is simply a Brownian motion experiment. Right? If you apply Ito's lemma to sort of that log, you get this term. So Z of t, the mispricing process, is a process which is going to be decreasing on average. We're going to force this delta to be negative. It comes from the drift of the price downward of the ask price, but also the drift of the underlying asset upward, which again creates a force for the two to intersect. And then there's a convexity adjustment that comes from Ito's lemma for those who know what that is. But this Z of t is simply a Brownian motion with volatility sigma and with drift given by this net drift rate delta. So our assumption here is that there are arbitrageurs or searchers or whoever. They are constantly scouring the markets and monitoring both what's going on in this particular auction and also what the market price or the fair value of the asset is. And in general, they will buy if the price they can buy at AFT is worth less than the value of the asset, right? And so one particular way to an equivalent way to phrase that is if the log mispricing is negative. However, because we're going to be operating on blockchains, they can only trade at instances of block generation, right? You can't trade continuously. And so again, following earlier work on a lever in the context of a discrete Poisson blocks, we're going to assume that the blocks are generated according to a Poisson process with a mean interarrival time of delta t. So this would be a pretty good model for proof of work. Proof of work is basically Poisson, modulo difficulty adjustments or so on. It is not a good model for proof of stake. Proof of stake is typically deterministic times between blocks. However, it's important for tractability here. So we're gonna make that assumption anyway. And we're also going to assume that the drift for that mispricing process is negative. If you recall, the mispricing process had this form. It's being pushed around by this drift. We're only going to trade if this eventually becomes negative at some point, right? And so a sufficient condition for this to eventually become negative and for it to eventually trade with probability 1 is that the drift is less than 0. So we will make that assumption. And I'll just point out practically, if you look at sort of what the values of these parameters are for, let's say, trading ETH versus USDC and so on, this mu and this half sigma squared, these are, maybe 1 to 2 orders of magnitude smaller than the kind of values you pick for lambda. So this drift is really dominated by the price decay that the auctioneer chooses. And so we're going to view this as in the control of the auctioneer. It's got to be positive, but they can decide how positive to set it. Right, so the auctioneer has to pick 2 parameters. They have to pick their initial mispricing. In other words, what's the initial log price difference between the offer price at time 0 and the market price? And they also have to choose what is the overall drift for this mispricing process. Right. So what does the analysis look like? So here's sort of basically the picture in cartoon form. The x-axis is time. The y-axis is price. The red curve you should imagine as an exponentially decreasing curve. That's the asking price, right? So that's coming down over time. The blue curve is my approximation of a geometric Brownian motion. That's wiggling all over the place. Here we had an auction which started at a higher price than the market price, started decreasing over time, and at this black point, the values crossed. So ideally, an arbitrageur would come in and instant after this, when PFT is higher than AFT, would sort of trade against this. But unfortunately, no block was generated then, right? So the next block is this time over here, and what you can see is along this sample path, at that point, the fair price is actually higher than the then current offer of the in the auction, and so this is kind of a loss, right? This is an efficiency loss. Like this. A Dutch auction is going to settle at a price which is less than the publicly observed fair value. So in that sense, the seller has taken a loss. And so that's what we want to model. That's what we're going to call loss versus fair, right? So the idea is if we define tau f to be the fill time, that's the intersection of 2 events. Number 1, it has to be a Poisson arrival time because we posited that we can only trade at times where blocks are generated according to a Poisson process. So it has to have that property. It also has to have this second property that the mispricing is negative. Right. So if this is the first time where that happens, our loss is going to be simply what was it worth at the time minus what did we pay for it. We're going to mark that relative to what its value is at the time. So it's going to be a relative efficiency loss. It's going to be positive because, again, we're only going to trade when PFT is greater than AFT. And conveniently, it can be expressed simply in terms of the mispricing. It's 1 minus e to the log mispricing at the time. So that's the idea of loss versus fair. And at the same time, we're also going to be concerned with how long it takes to trade. So we're also interested in the expected time for this event to happen where the auction is filled. And again, under the assumption that the drift is strictly positive, it will be filled in finite time and with a finite expectation of that time. So that's our setup. Main result is that we have closed form expressions for all this. They're here. Don't read them too carefully because I'm going to go through the more important ones in a moment. But we have explicit closed form expressions. I'll walk you through the first one. So again, we're looking at two things: loss versus fair and fill time. Let's start with the loss versus fair. We had two regimes here. One is if the initial mispricing is positive. That means that you start at an asking price higher than the fair value. And the second regime is the opposite. You start at an asking price lower than the fair value. We're primarily interested in the first case because that's typically what you would do. You would start at a higher price than what you think it's worth. And interestingly, if you start at a higher price, it turns out that your loss versus fair doesn't matter at the price that you start at, right? In other words, this expression here does not involve any Z zeros, right? And if you think about that for a second, it makes sense, right? And it has to do with Markovianness of the mispricing process and memorylessness of the Poisson. In particular, our mispricing process, Z of t, is continuous, right? It's only evolving according to a diffusion. It's a Brownian motion with drift. And so at some, like if we start out with that process positive, we're going to trade where it's negative. At some point in between those two, it has to cross zero. Right. And if we go to that point at which it crosses zero, at that point, we know that the Z value is zero. And because it's Markov, the history doesn't matter anymore in terms of the evolution of Z. And also because the Poisson is memoryless, the amount of time to the next arrival is the same as when you started. It's again just exponentially distributed, right? So because of that, you can split your time to fill to the first time that you get to zero, and then the time from when you get to zero to the time when you eventually fill. And in other words, what happens before you get to zero doesn't matter. Right, so in this region, we see that it's completely flat, right? No matter how high I set my initial price, it doesn't influence my my loss versus fair. In the other region, which is a different formula, not that formula, it does matter. And the lower you set your price, the more you expect to lose, and that's intuitive also, right? If I set my price way below the fair value, odds are I'm not going to get a fair price. So that's in terms of the dependence on the initial mispricing. There's also dependence on the drift. And again, this is largely in control of the auction seller. We see in general that the higher your drift is, the more you're going to lose. And that makes sense also. If your drift is very high, you're probably lowering the price very aggressively, and the price movement in between blocks is going to be larger, and you expect to lose more versus the fair value because of that fact. So all things being equal, to sort of minimize your efficiency loss, you want the drift to be very, very slow. On the other hand, if you look at the expression over here, and you make delta sort of very small, and you imagine delta t is very small, you'll see that this is actually lower bounded by sigma square root of delta t over 2. And that's the standard deviation of returns over half of the block time. Right, so I like to think of standard deviations as maybe typical realizations of a random variable, and so this is kind of saying that you can't get it below sort of what a typical return would be over half a block time, and that makes sense also, right? Because again, the core friction or inefficiency is coming because we can only trade at block times, and the prices are moving in between block times in a way that we can't capture. So that makes intuitive sense. But what's the implication? The implication is if you want auctions that are efficient. For example, if you have an asset with 5% daily volatility and you want to lose less than 2 basis points, there are sort of fundamental constraints on the block time. With these numbers, for example, you need a block time of less than 2.75 seconds. Right? Time to fill. Again, sort of similar patterns. I'm showing you here the case where the mispricing is positive to begin with. We see in general that as you increase the mispricing, as you start out higher than the original price, it takes a longer amount of time to fill. On the other hand, if you increase the drift rate, you sort of fill faster. This is a little bit the opposite pattern of what we saw before. So in general, there's going to be a trade-off. In general, you can pick your parameters, again, Z0 and the drift delta, you can pick them to be an efficient auction, or you can pick them to be a sort of a very fast auction. In both cases, there are lower bounds, right? Your time to fill is always going to be bounded below by the block time, because you can't fill until the next block. And we already argued that the loss versus fair is sort of bounded below. And this is the trade-off curve you see here. So here, I think I did it with 5% daily volatility and 12-second block times. And you can imagine solving an optimization problem like this to get a point on that, where here theta is a trade-off parameter in terms of how you value trading quickly versus not losing much money. This is a case where the initial price is known. Maybe a little bit more realistic if you're doing this on chain. Maybe the official the market price is not known, right? So maybe you have a prior on let's say what the initial market price is, like it's a log normal or something like that. In that case, you can do the expected version of this, where I'm taking an expectation over given a choice of the initial price, what is the actual mispricing? Because again, I don't know the fundamental price. And in this case, we can do these expectations in closed form as well. They're just somewhat lengthy, so I didn't put them on the slide. Okay, gradual Dutch auctions. Let me briefly sort of discuss this. The idea of a gradual Dutch auction, we're going to consider a continuous variation. We have a seller that's sort of generating auctions at a continuous rate, at a rate R per unit time. Each of these auctions is a separate Dutch auction, which is kind of decaying. And so, for example, if at some time t, if I want to trade a quantity q, I have to maybe go back, and t is the oldest auction that exists. That's going to have the best price. I have to go back Q over R units of time to get my quantity, and I can integrate what are the prices of these auctions. They're all decaying at the rate lambda, and you get a particular kind of expression. So sort of kind of the way to think about gradual Dutch auctions is I have this A of t, that's the best offered price, the best ask price. That's exponentially decreasing over time. Whenever a block is generated, there's a trade. And the trade trades through all the available Dutch auctions until the best ask price is matches the price P of t, and then you get geometric decay again until another block is generated, and again the blue curve is higher, so it eats through there, and then you get geometric decay again. So it's a combination of the geometric decay, but the process simply repeats because you're constantly selling more. And in this case, what's nice is that the mispricing process is a jump diffusion. So it has a steady state distribution. So details of this aren't so important. But what is important is we can get the same kind of trade-off that we saw before. So in particular, if I define two processes, the volume process at the top is the total dollar volume traded over a certain amount of time. The ARB process is the cumulative efficiency loss. So this is how much the arbitrageurs have made over that time. We can compute the rate at which these processes are growing, the instantaneous intensity, and we get expressions that make sense. I won't parse them for you, but one thing I'll note is the amount of money you lose to arbitrageurs is simply the amount you trade times the same loss versus fair that we had before. Right, and again, that makes a lot of sense. What I argued before is for a single auction, you're going to lose proportional loss versus fair. Here, this is saying simply many auctions in combination, you lose the same amount. Again, the goal here has been to analyze this very widely used primitive in DeFi and quantify the MEV that arises. We get nice closed form expressions, and they can be helpful in terms of parameter selection.
Yeah, time for maybe one question.
Yeah.
So I've seen some Dutch auctions where the price decrease is per block rather than per time step. I'm sorry, I'm just wondering if you could, how that would affect the analysis.
I haven't thought about it. I think it's,
The benefit there being you don't need like a oracle, like if it's a purely on-chain Dutch auction, right? You can just.
you don't need a time oracle.
You don't need an oracle, exactly.
Yeah, I haven't thought about that, that particularly. Max?
Yeah, so I guess in the context of multi-block MBB, the Dutch auctions seem very vulnerable because if you cross and you're very close to the fair price, your Dutch auction is very close to the fair price when you cross. There's like a very strong incentive to delay. I
Yeah.
wonder if that could be like included in the model as well.
Yes, so we actually quantified that, but we did it recently, so I didn't get in the slides. But basically, the idea is you can observe if you know the current market price, you can observe how much money you would make if you traded right now, you'd make that much. But if you were also the proposer for the next block, you could do not exactly this calculation, but a related calculation for how much you expect to make in the next block, and you'll expect to make more. So the difference of those two would be what the proposer of the next block would be willing to pay to censor the current block. And we can compute that quantity.
Is it always more
It's always more.
for the first block?
Yes.